Okay, can you hear me? Yes? Okay, cool. So if you're ready, let's start. Today the lecture is lecture 7, SIMD processors and GPUs. We are going to talk about one processing paradigm that takes advantage of a regular parallelism in our applications. Last week, as you remember, we had 2 lectures about DRAM. In the first lecture, Professor Mutlu explained the main memory and DRAM fundamentals, and that was on Wednesday. And on Thursday, we had 4 interesting talks about the research that we have in our group related to DRAM. These 4 talks were given by Hassan, Minesh, and Jeremy. So this is the agenda for today. We are going to talk about SIMD processing, including vector and array processors. We will see they are based on the same principles, but they have different characteristics, and we are going to study them. And then we will talk about the special type of SIMD processors that actually combines characteristics of both vector and array processors, and these are the graphics processing units that are the, let's say, the current form of SIMD processing and most successful form of SIMD processing these days. So both SIMD processors and GPUs take advantage or exploit data parallelism. We are going to see over this lecture that they are very good at exploiting regular data parallelism. So every time that we have an array of data elements that we have to process, we can use vector or array or processors or GPUs, and they are going to perform especially well when the parallelism is regular, when the computation that we have to perform on every data element is the same. Before we go into the details, let's first talk about the Flynn's taxonomy of computers. I'm pretty sure that you're already familiar with this. Mike Flynn in 1966 published this paper where he classified computers according to 2 dimensions, and the 2 dimensions are instructions and data. The first category is SISD, single instruction, single data. It's the case where we have one single instruction that operates every cycle on one single data element. This is like the traditional CPU model, right? Where we have sequential execution of instructions on different data elements. The second category is single instruction, multiple data. And this is what we are going to talk about today, about including array processors and vector processors. And here, the thing is that we have one single instruction, and because the workload that we are going to operate on has inherent regular data parallelism, with one single instruction, we are going to be able to operate on many different data elements at the same time. Third category is multiple instruction, single data, and this is like a very special type or very particular types of processors that have well, some specific characteristics and some specific applications. Among these MISD processors, we have systolic arrays that you might be familiar with them. They are actually being used very much these days because they form like they are like the basic structure of the Google Tensor Processing Unit that is used for training deep neural networks. We also have streaming processors here, and another type in this category could be the Micron's automata processors. And the last one is multiple instructions, multiple data. This corresponds to multi-threaded architectures and multiprocessors. Here we are going to have several threads or multiple threads of execution, and they are able to operate on different data and actually follow completely different instruction streams. But let's talk about SIMD in this lecture. So, as I said, for SIMD processors, it will be good that we have inherent data parallelism in our workloads, because concurrency arises from performing the same operation on different pieces of data. That's what we call SIMD. Examples. You have an example there, the dot product of two vectors. We will talk about it later, but if you want an even simpler example, just think about incrementing the elements of one vector, of one array. You have maybe 1 million elements in your array, and you just want to increment all these elements. So we're going to execute the same operation on all the data elements of the vector. Or think about vector addition. Two arrays, each of them 1 million elements, and we need to add element by element. So these are like the like the ideal cases for SIMD processors. In contrast with data flow, you're already familiar with data flow architectures. In data flow architectures, actually the concurrency does not arise from operating on different data elements at the same time, but on executing different operations in parallel. And also, in contrast to thread or control parallelism, that could be something like SIMD, right? Multiple instruction, multiple data, where we could have different threads of control executing in parallel. SIMD, as I said, exploit operation level parallelism on different data. It's a form of exploiting instruction level parallelism. What is instruction level parallelism? The ability to execute different instructions at the same time, and this is also a way of doing it, but the only particular thing is that the instruction that we execute is the same on all the different data that we operate on. Okay, so SIMD processing, operating on multiple data elements in time or in space. We are going to have multiple processing elements, and these are going to arrange in different manners. We talk two possible different manners. That's why we talk about the time-space duality. This results in the two possible SIMD processors that we can have and that we are going to study in this lecture. The first one are the array processors. As you will see, in array processors, one instruction operates on multiple data elements at the same time using different spaces, and the other one are the vector processors, where one instruction operates on multiple data elements in consecutive steps using the same space. We have a nice pictorial representation of array and vector processors, and we are going to discuss this a little bit more in detail. So first observe the code that we have here, this instruction stream, and can you see the pointer? Yes. Okay. So in this instruction stream, you can see a load instruction. In this load instruction, we are accessing 4 elements of array A, and we are storing them in a vector register, VR. Then we are going to increment the contents of vector register VR. So that's what we are doing with this addition, this vector addition operation here, or vector addition instruction. Then we have a vector multiply. We are multiplying by 2 each of the elements in the vector array, and when we are done, we store the result in array A again. So these 4 elements in array A. The way that these 4 instructions are executed for 4 data elements in array and vector processors is different. Here you have your timeline. And in an array processor, the very first instruction that we will issue in the first cycle is the load instruction. And as you can see, the 4 processing elements that we have in the array processor are executing the same load, the same instruction on different elements, because we have 4 elements, 0, 1, 2, 3. Each of the processing elements takes care of loading each of the 4 elements. As soon as we load from memory into the vector register, we can execute the addition operation. And that's what we have in the second cycle. In the third cycle, the processing elements will execute the multiply operation, and in the fourth cycle, they will execute the store operation. This is how the array processor will execute these 4 instructions. And what about the vector processor? In the vector processor, we have 4 units, 4 processing elements, but as you can see, each of the processing elements is specialized on one specific operation, on one specific instruction. So the first thing that we will do in the first cycle is issuing the load, or executing the load for element 0. And this is something that will be done by this load processing element that we have here. In the second cycle, assuming that we have already got the value A0 from memory, and we have it already in the vector register, we can execute load for element 1 and the addition for element 0. In the next cycle, in the third cycle, we will have load for element 2, addition for element 1, and multiply for element 0, and so on. Right? So, if you observe what we are doing, and this is the time-space duality, what we are doing is that here in the array processor, we execute the same operation at the same time, while in the vector processor, we execute different operations at the same time. And in space, we have different operations in the same space, because these processing elements are able to execute any of these 4 instructions. And in the vector processor, we have the same operation in the same space. So that's the main distinction between array and vector processors. We can also compare SIMD processors, and in particular in these next 2 slides, we are going to compare SIMD array processors to very long instruction word architectures, because they are also a form of exploiting instruction level parallelism. Actually, the reason why these VLIW architectures were proposed and were designed is because in many workloads there is not so much inherent regular data parallelism, but still there is irregular parallelism that can be exploited. So that's why what VLIW architectures did. For them to work correctly, they needed a smart compiler that was able to identify instructions that were independent in the code when compiling the code. And this way we could have something like this. For example, here you see the program counter is pointing to one instruction that contains 4 different operations. But if you observe these 4 different operations, they are operating on different elements. This means that there are no dependencies between these 4 operations. In contrast, in the array processor, what we have is a single instruction and a single operation that is going to be executed on different data elements. That's what we have here. Our program counter is pointing to this single instruction here, add, and we have 4 processing elements, and these processing elements are going to execute this instruction on 4 different data elements. It's okay? Any questions so far? Okay. Yeah, let's focus more on vector processors. Even though we are, over the course of the lecture, we are going to, all the different concepts are going to be explained by using the vector processors, but most of them, they also apply to the array processors. So vector processor, a vector, as you know, is a one-dimensional array of numbers. And many applications, scientific and commercial programs use vectors. This is something that you already know. Here you have a very simple code that we are going to use as a running example. In this simple code, what we have is a for loop that operates, that goes through 3 vectors, 50 elements of 3 vectors. And what we are doing here is calculating the element-wise average of A and B and store the result in C. So because all the 50 operations that we need to execute here are exactly the same, they can be efficiently executed on a vector processor. There are only some basic requirements that should be fulfilled, and actually are fulfilled here, is that we need to load and store vectors and from memory or to memory, and we will use vector registers for storing, for storing intermediate data. And these vector registers have a certain length. So that essentially is going to be related to the number of processing elements that we are going to have in our SIMD processor. Let's take a very quick look at this with one example here. Okay. So we have some code. In particular, let's think about a vector load instruction. And with this vector load instruction, we want to access memory. This is our memory. Our memory has, n elements, and all the elements are stored linearly in memory, something like this. This is element 0. This would be, this is element 0, element 1, 2, and so on. Okay? So, when we want to execute this vector load instruction, it's important, one of the first things that we need to define is the vector length, which is the number of elements that we are going to operate with one single instruction. And as I said before, it's related to the number of processing elements that we have in the vector processor. So the second thing that we have to define is the vector stride. The vector stride defines the distance in memory of the elements, between the elements that we are going to operate on. Let's start with the simplest case, vector stride equal to 1. This means that when we execute this vector load instruction from array A, and let's consider that array A starts here in address 0, what we will do is reading or loading from memory vector length elements that are at distance 1. So for example, if our vector length is equal 4, we could be, with this vector load A instruction, we would be loading these 4 elements into the vector register. So what we do here is calculating addresses and accessing these addresses. Actually, if our vector length is 4, it would be something like this. Okay? Another possibility is that we have a different stride. Let's say that our stride is 4. If our stride is 4, then what the addresses that we will access are A0, A plus 4, A plus 8, A plus 12 for the vector length equal to 4. So we would be reading this element and this element, and this is probably 8, this element. So we will be accessing here, 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 and somewhere else. Okay? Yeah, so this, let me go back to the slides. These are like some of the basic requirements. We will talk later also about the vector mask, that is going to be useful for conditional operations. So, a vector instruction performs an operation on each element in consecutive cycles. The vector functional units are pipeline, and in each pipeline stage operates on a different data element. This allows us to have deeper pipelines, but it is important to fulfill some requirements. First, intra-vector dependencies are not allowed. So if we want to operate on, let's say, 4 elements, as we had in the previous example, or vector length is 4, we should make sure that there are no dependencies between the operations that we are going to execute on the 4 elements that are in the vector register. Second is that we won't have control flow within a vector, so there are no branches. The four operations are going to be executed at the same time. We need to know the stride, as you have seen in the previous example. A stride will be 1, or a stride will be 4. And also, knowing this stride has some benefit. For example, the fact that we can have efficient prefetching. Prefetching, I guess you all are familiar with the concept of prefetching. Essentially means going to memory and bringing some data that is not going to be needed immediately, but after some time. And this is something that is really possible in vector processors, because we know what's the stride. So if we are operating on 4 elements, and then we will have to operate on the next 4 elements because we know the stride, for example, a stride equal 1 or a stride equal 4, it will be possible to prefetch. It would be possible to go to memory and start bringing the data from memory before it's needed. So this is one of the vector processor advantages, but there are more. Because there are no dependencies within a vector, pipelining and parallelization work really well, and we can have very deep pipelines. We can have many stages in our pipeline, and we won't need to stall the execution of any instruction or forward data, because we know that all the elements, all the operations that are in the same vector register are completely independent. Each instruction generates a lot of work, and this means that every time that we go to memory and fetch one new instruction, we are going to be able to operate on many data elements at the same time. And this, the good thing is that reduces the instruction fetch bandwidth requirements, because with one single instruction we will be operating on V length, for example 4 or maybe 32 elements at the same time. So probably one potential benefit from this is that because we don't need to go to memory so frequently, we might have smaller caches, and still our processor will give us very good performance. Another advantage is that we have highly regular memory access patterns, and this is, for example, in GPUs, it's like the ideal way of accessing memory to get the maximum possible bandwidth. And we don't need to explicitly code loops. In principle, there are no loops here. We will only use loops when the size of the vector that we need to, the total number of elements that we need to operate on is larger than the vector length. We will talk about that later. But unfortunately, vector processors also have some disadvantages, and they are, as we already know, they are very good for regular data parallelism, but they are very inefficient if the parallelism is irregular. And still, there are many applications in which we have irregular data parallelism or even sequential execution. So, for example, when you try to search for a key in a linked list, it's an inherently sequential operation. You have to go step by step until you reach the desired key. And this is something, one particular operation where a vector processor or a SIMD processor is not going to perform well. And it's not the only disadvantage. Another disadvantage is how difficult it's or can be to program them. And this is one excerpt from this paper by Fisher in 1983. It says, to program a vector machine, the compiler or hand coder must make the data structure in the code fit nearly exactly the regular structure built into the hardware. That's hard to do in first place and just as hard to change. So, because if we really want to take full advantage of the processing capability, processing power of the SIMD processor, we need to have very regular data structures that can be accessed in a very efficient way and can be operated on in a very efficient way. Another limitation is related, or potential limitation is related to the bandwidth to memory, because now we are going to operate on so many data elements at the same time. We really need to have a memory that is able to give us all the bandwidth and all the amount of data that we need every cycle, right? And this is fine as long as we do enough operations on the data elements that we read from memory. So if our arithmetic intensity or compute intensity is high enough, this means that every time that we read something from memory, we execute several or many operations on this data, everything will be okay. But if our computation is very lightweight and we are just essentially moving data, we will be always accessing memory, and this will overwhelm the memory bandwidth. One way of dealing with that is using memory banks that we are going to see next. Okay, let's talk a little bit more in depth about the vector processors. We have already talked about the vector registers. In each vector data register, we hold n m-bit values. For example, n might be 32. We might have 32 elements in the vector register, and m might be 64 bits, for example, if we are operating on double precision elements. We have vector control registers. We have already talked about them. VLIW, that is the number of elements that we have in the register. Stride, the vector stride, what's the distance between the elements that are going to be accessed from memory. And then we have the vector mask. The maximum VLAN is a number that depends on the hardware. Let's say it's n. And the vector mask, we will see one example later, but what we are going to do with the vector mask is masking the operations that we execute on the different elements that are stored in the vector register. And this allows us to do some conditional execution. For example, in case, I don't know, the example here is that we might want or not to operate on elements that are equal to 0. So depending on this predicate that we have here, the outcome of this predicate that we have here, the corresponding bit in the vector mask will be 1 or 0, and this will mean that the operation is actually executed or not. About the vector functional units, we have already mentioned that one of the benefits of vector processors is that they allow us to have a very deep pipeline, and the fact that we have a deep pipeline, we have many stages in the pipeline, means that we will be doing less things in each of the stages, and this way we can have a faster clock cycle. So we can operate at a higher frequency. Yeah, and this is possible because we start from the assumption that the operations that we are executing on the vector register are independent, because there are no dependencies among the different data elements. Okay, here in this slide you can see, or one example, or first example of vector matching. This is the CRAY 1. Yeah, as you can see in this figure here, we have the vector registers here on the left. We have some vector functional units here for floating point. We also have some scalar units, because even though this is a vector machine, still we need to have, or it's good to have scalar processors, because that's something that we already mentioned. For sequential computation, for scalar computation, the vector processors are not good, so it's still good to have some cores or some processing units that can execute scalar operations. And here on the left you have the memory. That actually is it's a memory with 16 banks. We will go into the details later. Meanwhile, let me show you this picture from the CRAY that we have here in ETH. It's in CAP, in the building where we are. So yeah, maybe you have already seen it, or you might want to visit it. It's like a very beautiful machine indeed. And here you have some slides about this CRAY XMP. Actually, if you compare this figure here with the one that we have just seen for CRAY 1, you might see that it's very, very similar. You have some design details. For example, this XMP28 has two CPUs, has two scalar cores. Here you have some details about the functional units, address functional units to calculate the address to access memory, scalar functional units, vector functional units, and some more configuration details here. And in this slide we have Seymour Cray, who's called the father of supercomputers. Yeah, he said something like this: if you are plowing a field, which would you rather use, 2 strong oxen or 1024 chickens? Well, it depends on your computation, right? So if we are going to operate on many elements at the same time, probably we will go for the chickens, because, I mean, assuming that the computation that we need to do on the different data elements is completely independent. If there are some sort of irregular computation or some sort of scalar or sequential computation, we might need to use the 2 strong oxen. Okay, let's go back to the CRAY 1, and here in the CRAY 1, as I said before, we have 16 memory banks. So let's take a look at how are we going to use these 16 memory banks, and let's take a look at how we load and store vectors from and to memory. Because this is a vector processor, we need to access, read and write multiple elements at the same time. And we already know that the elements that we are going to store in a vector register are in memory, and there is a distance between these elements that we are going to access, so we are going to operate on. And this distance is the stride. For now, we are going to assume that the stride is equal to 1. And we are going to see how this these V-length elements that we have in memory at a distance 1 from each other are going to be loaded in consecutive cycles. Because if we really want to be efficient, we should try to be able to access each one of these elements in one single cycle. But unfortunately, memory is not usually that fast. We cannot access memory in just one single cycle. We will usually need more cycles to access memory. In CRAY 1, for example, the latency to access memory was 11 cycles, and this is the value that we are going to consider in the example that we are going to see next. So what should we do if we want to have one ready element every cycle, but our memory takes longer than one cycle? What we do is banking the memory. What we do is interleaving elements across multiple banks. We're going to see how these multiple banks are operated. Instead of having one single monolithic memory, one single monolithic array, what we do is chopping this entire memory into different parts. In particular, in this example, 16 parts, 16 banks. And for each of these banks, we have one memory address register where we are going to have the address that we want to access in each of the banks, and also we have a memory data register where we are going to store the value that we read from memory or write to memory. All these banks, as you can see, are going to share the data bus and the address bus. So let's take a look at how this is going to work here with one example. Yeah. Okay. So if we have one single bank, if we have a monolithic array, it will look something like this. This is address 0, this is address n-1, for example. This is our entire memory, and here we have address 0, address 1, and so on up to address n-1, right? If we want to access this memory, read or write, we need some memory address register, and we need some memory data register. With the memory address register, we will select a specific address here, and if we are reading, the corresponding value will be moved from the memory to the memory MDR, memory data register. This takes a certain number of cycles, m. In our example, this is going to be 11 cycles. It's a single port. Why is it single port? Because we can only access one element at a time. We can only have one address in the memory address register, so that's why we say that it's single port, and it's just one single bank. What we can do in order to have a more efficient access to this memory is dividing this memory into banks. In our example, we are using 16 banks. This is bank 0, bank 1, bank 15. And now what we do is storing the addresses or storing the values corresponding to the different addresses in an interleaved manner, so that address 0 is bank 0, address 1 is in bank 1, address 15 is in bank 15, and address 16 is again in bank 0, and this would be address 31. And now in each of these banks we have our memory address register, memory data register, memory address register, and memory data registers that are connected to the corresponding bank. All these banks share the same address and databases. So memory address registers are connected to the data bus. Memory data registers are to the address bus. Memory data registers are connected to the data bus. And now let's see one example of how are we going to access all these 16 banks. What we can do, because we will still have the same access latency. The bank access latency is going to be still m cycles or 11 cycles in our example. Let's assume that our stride is 1. If our stride is 1, we will, in the first cycle, cycle 0, we will issue the first load. In this case, so if we are accessing, for example, element 0, we will issue this load to bank 0. Right after we do that, in cycle 1, we can issue the load to bank 1, and in cycle 2, we can do the same for bank 2. Because, you know, in this cycle, we started the access to bank 0, and our bank latency is still 11 cycles. We know that in cycle 10, we will have data element 0. Right? And because in cycle 1 we started the access to bank 1, right, 1 cycle later we will have data 1, and then 2, 3, etc. Still our bank access latency is 11 cycles, but our throughput is, or bandwidth is 1 element every cycle, thanks to the use of the 16 banks. And this is how vector processors are able to access memory in a very efficient way. There are obviously some limitations. And what's the limitation? It is related to the stride and how this stride relates to the number of banks. Because now let's go to the worst case scenario in which our stride is equal to 16, what means that we are going to operate on elements 0, 16, 32, and so on. And it turns out that all these elements are stored in bank 0. So it will be impossible to avoid the entire bank access latency for all the elements that we will be reading from bank 0. So we will start the access to element 0 in cycle 0. In cycle 10, we will be able to obtain data element 0, but we cannot start the access to data 1 until cycle 11, and we will have data 1 in cycle 20. So we unavoidably are have to deal with the entire bank access latency for the access to all the elements. Okay, let's go back to the slides. Is that clear? You have any questions? Okay, cool. So so this is what we have just explained. Memory is divided into banks that can be accessed independently. In principle, and in the example and here in the slide, what we see is that all the banks are sharing the same address and the same data bus. The reason for that is cost related reason, because if we want to have more buses, or we want address or data buses, we will need to have a larger number of pins, and this entails more cost when building our chips. And but still, because we have the banks, we are able to start and complete one bank access per cycle. If we have n banks, we will be able to sustain n parallel accesses. And yeah, we have already talked a little bit about that, but here you can see a little bit more detail about how the addresses are calculated, because we will have one base address that is the address of the array, the vector that we are accessing in memory, and we have some stride that give us the distance between the elements that we are going to access. We need to have this address generator that is generating the address that will be stored in the memory address register and will be the address to access all the different banks. So here we just need one address generator because we are going to start the access to each bank in a different consecutive cycle. This is how we calculate the address. The next address is the previous address plus the stride. And one important, several conditions that we should fulfill in order to sustain this throughput of one element per cycle is that, in principle, we are assuming that the stride is 1. Also, that the consecutive elements are interleaved across banks. And let's first explain what this means. Let's go back to here. So what this means, having consecutive elements interleaved across banks, means that we have element 0 here, we have element 1 here, we have element 15 here in different banks. Consecutive elements are interleaved across different banks. We could have a different data mapping, right? And for example, have address 0 here, address 1, address 2, and so on. So in that case, having a stride 1 wouldn't be a good choice, right? Because all the elements with a stride 1 would be in the same bank, and then we will run into the same situation as we had before with the stride equal to 16. Okay, and the last condition that should be fulfilled is that the number of banks is greater or equal to the bank latency. That's essential. As you can see, you have just seen in the operation, this access is going to be really efficient if the number of banks that we have here is enough to hide the latency of issuing all these accesses. And before we finish the generation of the address and the issue of the vector load to all the 16 banks that we have, we are already receiving the first data element 0 in this case. Okay, let's go for a little bit more detail with this code example. It's the same code that we had before, this element-wise average. And now, in order to start, what we have here is the scalar code. Yeah, so if we, this will be like our assembly code. And you have all the instructions here that we need to execute this high-level code that we have here, and on the right-hand side you have the latency of each of these instructions. So the first instruction is move. We are storing move immediate. We are storing in register R0. We are storing 50 because it's the number of iterations that we will carry out for this loop that we have here, because it's exactly the number of iterations that we have in our original high-level code. Then in registers R1, 2, and 3, we store the addresses of arrays A, B, and C. And then here, we start the loop that will be executed 50 times. So as you can see, the first instruction is a load instruction that accesses memory, the address, the address contained in register 1, and reads from memory and stores the value in register 4. We assume here that we have auto-increment addressing, so just assume that the content of this register is incremented automatically, just for not having like increment operations later. just for simplicity of the explanation. Then we have the second load where we access the address pointed by register 2. In this address we have vector B, array B, so we go to memory and we store the value in register 5. We need for both operations 11 cycles is the access latency that we are considering to memory in this running example. Then as soon as we get we have register 4 and register 5, we have the corresponding values there, we can execute the addition and store the result in register 6. This takes 4 cycles, and then we shift right. You know that shifting right 1 bit is the same as dividing by 2, so that's we need 1 cycle to do this shift, and when we have the final result in R7, we will store the value in the corresponding memory address pointed by register 3. We repeat this 50 times, and that's why we need to have this decrement and branch if not 0. So we are comparing we are checking that the value, so we decrement and we check that the value of this register is 0 or not. If it's not 0, we jump and go again to execute the loop. So if we count the total number of instructions that we need here, the total number of dynamic instructions is 304. Essentially is the 6 instructions that we have in the loop, because every 6 instructions we will jump for 50 times. This is 300 instructions plus the 4 move instructions that we have in the beginning. That's why we have 304 dynamic instructions. And we can count, because we know the latency of each of these instructions, we can count how many cycles will we need to execute the entire computation. In the first case, assuming that we have a very simple monolithic memory with one single bank, we cannot pipeline the access to the different addresses, to the these 2 load instructions here. So we would need 2 times 11 cycle to access the source operands, right? So that's why total number of cycles that we will need per iteration will be 40, and the total number of cycles is 2004. Because we are going to use banked memories banked memories later, let's assume that we already have a banked memory. We have, for example, 16 banks. If we have 16 banks and we assume that these 2 accesses, these 2 load accesses go to different banks, then we can consider that both can be executed concurrently. So in that way, we would be saving 10 cycles in every single iteration, and the total number of cycles to execute our code will be 1,504 cycles. The question, why 16 banks? In this example, we just have 2 loads, so in principle we wouldn't need more than 2 banks if we want to have concurrent access to memory. But why 16 banks? Because this is what we are going to need for the vector processor, and we need 16 banks because something that we have already explained. We need 16 banks because 16 is greater than 11. That is the number of cycles that is our memory or bank access latency. So that's why we always have to find a number or to choose a number of banks that is greater or equal to the total number of cycles that we need to access memory. So, because the operations that we are going to, all the operations that we are going to execute in each of the iterations in this loop are independent, we can say that this is a vectorizable loop. This means that, this means what it means. It means that all the execution of every iteration is independent of the execution of any other iteration. So we can say that there are not there aren't loop carry dependencies here. And because that's the case, we can vectorize this loop. And when we vectorize this loop, the first advantage that you can see here is that we have a much more compressed code. We have the same number of operations in less number of instructions. Recall that this was actually one of the benefits of the vector processors, the fact that every time that we fetch one instruction from memory, from the, for example, the instruction cache, we will be operating on many elements at the same time, so we don't have so many instruction fetch bandwidth requirements. Okay, so this is our code. Observe that the two first instructions here are to set the value of the vector length. In this case is 50 because we have 50 iterations in the loop. The stride is 1 because, you know, for every iteration we increment this index I by 1, so that's why all the elements that are going to be accessed are at distance 1. Stride is 1, and then we have our vector load to access 50 elements from array A and store them in vector register V0, then next vector load to access array B, and then we can execute this vector add, have the intermediate result in vector register 2, then we shift right all the elements contained in vector register 2. We will have our final result in vector 3, and from vector register 3 we store in the final destination in array C in memory. Now here on the right hand side you can see the latency of all these instructions. The latency of the individual instruction of the individual operations is exactly the same. For example, 1 cycle in case of the move instructions, 11 cycles is the memory access latency, because now we have a vector processor. We are going to consider that we have a vector processor and we have a pipeline execution, not only in the access to memory thanks to the memory banks, but also because our functional units are pipeline. We will have the total number of cycles, the total latency to execute this load from memory will be 11 plus vector length minus 1. Let me just show you very, very quickly one example here. Oh, sorry. Okay. So for example, for the vector load, in cycle 0, we start the access to the first element, right? After 11 cycles, we will have data element 0. And then, one cycle later, in cycle 12, we have data element 1. In cycle 13, data element 2, and so on. And in cycle 60, we will have our last element. So observe that during this time, we are getting 50 elements from memory. And every time that we get one of these elements, they will go to the corresponding position in the vector register, right? But if you observe here, what's the total latency of this vector load is 11, that is the bank access latency, plus vector length is 50 minus 1. Okay? In case of a vector add, for example, if we have a vector add, in our example, the vector add has a latency of 4 cycles. The total latency for the 50 elements will be 4 plus vector length minus 1. So that's why we have these latency values here. Do you have a question?
If it's already pipeline, then we know also that the vector load data of V1 doesn't need this 11 latency.
If it's already pipeline?
Yeah, I mean, the vector load of V1 can be like also, doesn't that incur the 11 cycle latency?
Yeah, it incurs the 11 cycles because, I mean, you have to go over the entire pipeline, right? So, this is the thing. The very first access, the latency of the very first access to memory, same as the latency of the very first addition in your vector functional unit, you're going to see it completely because there is nothing else in the pipeline at that time, right? So you see, for example, in the case of the vector add, you will see the 4 cycles for the first, and because right after the first add for the first element started, you can issue the next add for the next element. As soon as the 4 cycle, these 4 cycles finish and you get the first result, you will only need 1 cycle more to get the next result, and then the next result, etc.
Yeah, you see the access latency on V0, but not on the V1 node.
Exactly. The access latency that you see completely is the access latency for element 0, same as the execution latency for this vector add or this shift right operation is the one corresponding to the very first element. But let me continue because we have a timeline in a later slide that I think that it will be much more clear. So yeah, so here you can count the total number of instructions is 7. So remember, it was 304 for the scalar processor. Here in the vector processor is only 7 dynamic instructions. And for now, we are going to assume that there is no chaining. Chaining means that there is no data forwarding, vector data forwarding. And this essentially means that we cannot use the output of one vector functional unit until all the elements in the output register are ready. So yeah, so this is for now we are not applying this optimization that we will apply next. So this means that before, so going back to the code, before we start executing this shift operation, for example, we need to make sure that all the 50 additions that this vector addition will execute have finished. So that's what no chaining means. Also, we assume that there is only one memory port. So recall that recall that in each of this bank memory we had or memory address register and or memory data register. This represents one single port because this means that every cycle we can only be accessing one single address. So that's what it means. We have just one single port and we are actually sharing the same port for loads and stores. And there are 60 memory banks. And this is how it will look. Let me actually show you here also with the DocuCam because I think it's going to be better as we will be able to see both the code and the timeline, and I think that it will be easier if I can fit everything here. Yeah, more or less. Okay. Yeah, I think it's okay. So yeah, so this is the timeline that I mentioned before. This first cycle here corresponds to this move instruction, second cycle to this instruction, and now we start the vector load. We will see the entire 11 cycles for the very first element, but because we have 16 banks, we can issue one load every cycle. So right after that, we will have so in this point in time, we will get we will get element 0 of array A, and one cycle later we will get element 1. One cycle later we will get element 2, and after 49 cycles in this point, we will have the 50 elements loaded into our vector 0, right? Because we have one single memory port, we cannot be loading two different vector registers at the same time. So we cannot start this vector load until this point. So that's why, again, we see here the entire 11 cycles plus 49. And because we have no chaining, that was one of the things that we, there is no chaining, remember, that's one of the things that are assuming here. We cannot start the execution of this vector add until all the elements from the first vector load and all the elements from the second vector load are in the corresponding vector registers. Right after that, we start the addition, 4 cycles for the first element, then 49 more cycles for all the 15 elements to be completed. Then we have 1 cycle for the shift right, 49 more cycles, and finally the final store, 11 cycles plus the last 49 cycles. In total, 285 cycles that are already a very good improvement, almost 7 times faster than our Scalar code was. Is it clear? Okay. Yeah, but we can still do it faster, actually. We will be able to do it faster if we allow our processor to chain to the forward elements that are, or results that are already produced, and forward them to the next or a different functional unit. And that's what we have here. So in this example, you can see this is a vector load. We are accessing memory and loading data elements in B1. And because we have a banked memory, every cycle we will be receiving one new data element from memory. As soon as we get one data element 0, for example, from memory, we can forward it to the next functional unit, that in this case will be the functional unit that executes this multiply operation. And same for the multiply to the addition operation. So it will be something like this. We have memory or load unit. As soon as this load unit gets the first element from memory that will be stored in vector 1, we can change it and use it as a source operand to this functional multiply functional unit. And as soon as we get the first result from this multiply functional unit, we can chain it to the next, that in this case is an addition. So what if in our previous example we apply vector chaining? This means that we don't have to wait for the entire load to finish before we start the execution of the addition. So as you can see, as soon as the second vector load finishes for the first element in this load, right after these 11 cycles, we can start the execution of the addition. And we can start counting these 4 cycles that we need for the execution of the addition. And as soon as we finish the addition for element 0 in the vector, we can start the shift register operation, right? Here observe that it could be the same. It would be the same for the store. We could start the store operation right after this cycle, because right after this cycle we have shifted one element, 1 bit to the right. So it's the same as dividing by 2, as you know. And right at that time we already have the final result for the first element in the array, right? But why can we start right here? Why should we wait until here?
Because the functional unit is busy.
Because the load unit, the unit that is accessing to memory, it's still busy generating addresses for this vector load, because we have one single memory port. Okay? So we can do it better if we add more memory ports in our bank. Yeah.
I mean, for data movement, I understand, but the addresses are also like concurrently written out the memory as data is moved out. The 11 latency and the 49, the addresses get written to memory simultaneously. So why doesn't the second vector load also can continue writing these addresses simultaneously out?
So I think I didn't get the question. Could you repeat?
The vector load, you write the memory addresses concurrently as you read out memory. So why can we continue this with the second vector load?
Oh, why cannot be also accessing with the second vector load?
Yeah, as writing out the memory addresses.
Yeah, so it's because we have one single memory port. We have one single memory address register and one single memory data register. In the memory address register, we need to have the address that we are reading or writing, and that address must be there. So we cannot have two accesses to the same bank at the same time. Let me show you the example. Actually, it's going to be easier if we see it here. So we have our bank memory, right? This is bank 0, and here we have bank 1, and here we have bank 15. And in the memory that we are considering, we have one single memory address register and one single memory data register. So if we want to access, read some specific address from memory, we need to have the corresponding address here in the memory address register. So this will be used by the first vector load. So the second vector load, assuming that obviously the second vector load also needs to access some element here in this bank 0, has to wait until the first vector load has finished and the memory address register is free. That's why we can do it better if we add one second port with its own memory address register and memory data register. And also, we can even have one third memory port with its own MIR and NDR for stores. So we can read two addresses from memory at the same time, and also at the same time we can write to some other address in memory. So that's what we can do in order to still improve, and we will have the same ports in each of the banks, right? Is it clear now? Okay, so if we apply that optimization, then we can end up having something like this. Only 79 cycles, because as you see, we don't need to wait for the entire vector load to finish in order to start with the second vector load, same as we don't need to wait for all these vector loads to finish in order to start with the final vector store. And that's why we are able to improve the performance of this code by 19 times compared to the scalar execution. Okay? Okay. Yeah, I think we can continue a few more minutes before we have a break. Let's discuss a couple of things. First thing, one question. What if the number of data elements is greater than the number of elements in the vector register? Because you see, in our example, our total number of elements that our code or high-level code was operating on was 50, and we say, okay, our vector length is 50, so we can operate on the 50 elements at the same time. But usually we will have to operate on more than 50 elements in real life. So what if we have to operate on 500 or 5,000 or 5 million elements? What will we do if our vector length imposed by the hardware is 50 or maybe is 32 or something? So yeah, we will have to use loops in this case. So we will break the entire loop, all the iterations of this scalar code, high-level code that we had. We will break them into as many iterations as necessary, and in each iteration we will be operating on vector length elements. Here you have one example, because sometimes it won't be, it won't be, the total number of elements that we have to operate on won't be divisible by the vector length of the hardware. So what if the data elements that we have are 527 and our vector length in our hardware is 64. So we will have to do something like this. First of all, 8 iterations with vector length equals 64, and then 1 iteration with vector length equal 15 in order to finish the computation, finish the execution for this tail of 15 elements. This is what is called vector strip mining, and this concept is related to a strip mining, that is a form of surface mining. Essentially means that if you want to access, access the deposit where the mineral, let's say for example gold, is, you have to remove all the residual materials that are on top of it, right? Like maybe sand or rocks or whatever. We have to remove them in order to go to what is really interesting. So that's something similar to what we have to do with these 15 elements that we want to get rid of them, execute them as soon as possible, or maybe at the end in the case of the vector processor, and then go to the real vector processing execution that will be taking advantage of the entire vector length of the 64 64 processing elements possibly that we will have in our vector processor. And then we have a second question here. What if vector data is not stored in a structured fashion in memory? Observe that as until now we have assumed that even though the data elements that we want to operate on might not be consecutively stored in memory, they are in a regular organization. They are at a certain distance, and every 2 consecutive elements are always at the same distance that is the stride. But unfortunately, this is not something that is always going to happen. In some specific applications, for example, when we operate on sparse matrices, we will need to use scatter and gather operations that allow us to use indirection. I think I'm going to give you this example very quickly, and then we will have the break. So let me quickly explain what a gather and scatter operation is. It's the type of operations that the type of memory accesses that will allow us to execute a code like this, in which you can see that there is some indirection here. So in order to give you an example, let me describe how we would access one sparse vector or one sparse matrix in memory. By the way, sparse matrices and sparse vectors, as you may know, are very popular these days. For example, they are used to represent graphs, to store, and graphs are like very important data structures in this era of the big data, right? So this is something that we are going to very frequently find these days. Assume that this is our array C. So if we go quickly back to the example, recall that we had array C, and we will access array C according to the indices that we are going to read from array D. So what we will have is that here we have array C, and interestingly, most of the elements in this array C are going to be 0, so we don't want to use them. We only want to use the elements that are different to 0. That's what we do when we operate on sparse vectors or sparse matrices. And maybe we have our first element different to 0 here in address 1001, and then the next one is in address 2050, and then the next one is here, for example, in address 3072. So in order to access this memory, these elements in memory, what we will do is using this array D, this kind of index array. And in this index array, what we have is the addresses where the elements that are different to 0 are stored. So that the elements in array D are pointing to the elements in array C. So when we access memory this way, what we are doing is going to first array D, reading this element, and adding this 1001 to the address of array C, so that we will be getting the value that is actually stored in memory. 4 in this case, then we will do C plus 2050, and we will get 10, and so on. So this is what we do with scatter and gather accesses, and here you can see some example code for a gather operation. First, we access array D in memory, we load the indices that are contained in array D, we load them in the vector register D, and then with this vector register D and using this load indirect instruction, we access array C and we store whatever we read from memory in array B, and then we can continue with the execution, with the computation. Next instruction is a normal vector load where we access vector B, then an addition, and finally the store in array A. And it's the same for a scatter example. You have one scatter example here. This is the index vector. This will be the array D in the previous example. This is the data vector. This is what we want to store somewhere in memory. Observe that the difference between the previous example and this example is that in the previous example we are gathering, we are reading from memory, from different positions in memory that are given by the index array, and here what we are doing is scattering. What we are doing is writing. So we will write this 3.14 in base plus 0, because the first index vector is 0, next index vector is 2, so we write this 6.5 in base plus 2. Okay? Okay, let's take a break, maybe 10 minutes, and we will continue. Okay, I think we can continue if you're ready. So, now we have one new question here. What if some operations should not be executed on the entire vector? So what if some operations, we just want them to be executed on some elements on the vector, depending on some predicate, right? For example, here, in this loop, what we have is some multiplication, but we only want to execute this multiplication if the value of the corresponding element in array A is different to 0. So in this case is where we are going to use mask operations, because this is where we are going to use this vector mask register that we already defined in the first part of the lecture. What we will do is having some instruction to evaluate the predicate, and depending on the value of the predicate we will set the mask, and then depending on the value of the mask we will execute the next instructions. This is what is called the predicate execution, and actually this is a way of implementing control flow. Instead of using branches, we use this predicate register, we use these masks. Next week, Professor Mudlu will explain branch prediction and control flow handling, and one of the ways of doing control flow handling is predicate execution. So I'm just going to introduce it here, and you will see it in much more detail next week. So here you have another example with masking. In this case, we have an if cell and if else. If AI is greater or equal than B, then we do C equal A, else we do C equal V. And the way that we implement this is by first comparing A and B, and depending on this comparison we will get 1, 0 or 1 in the corresponding bit for the corresponding element in the vector register. And we obtain V mask. Then we, in step 2, we store A into C for those elements that have 1 in the vector mask. Then we complement the mask, and then we execute the store from B to C. So as you can see, if A is greater or equal to B, as is these two cases, vector mask is equal 1, so we will execute this step 2. If it's not, like for example this case here, we will have to wait until we complement the mask, and then we execute this store in step 4. The way that we actually do this in hardware might be in a simple way. We calculate the mask, and then depending on the value of the corresponding bit in the mask, we will actually enable the write operation in the output register or not. So for example here, because the bit 0 in the mask for element 0 is 0, we won't enable this write, so this value that has actually this output operand that has actually been obtained after going through the entire pipeline won't be written into the final destination. And a smarter way, more efficient, will be to have this density time implementation, in which what we do is we first go through the entire vector mask, and we only issue those operations, in this case maybe those additions or those multiplications that corresponds to elements where the corresponding bit in the mask is equal to 1. So as you can guess, this is going to be more efficient. So in principle it will be better, but there are also some trade-offs, right? Because in this simple implementation we just need to feed all these input elements into the pipeline and get the output, and depending on the value of the mask we write or not. But here we need like a first step in which we need to go through the entire mask and then decide on the scheduling of the operations. Okay, let's go back to some more issues related to stride and banking, and now we're going to see another example, because we have been talking about how to access memory, how to access the memory banks, and how to access with different strides, but we have only considered 2 cases so far, right? One case was when stride was equal to 1, the other case that we had in the example was a stride equal to 16, where all the accesses went to the same bank. How are we going to have an efficient memory access? Do we always need to have a stride 1 to have an efficient memory access? No. With other different strides, we can also have an efficient memory access. And because the only thing that we need to ensure, if we want to be able to access all the banks at the same time, is that the number of banks and the stride are relatively prime. This means that they are not divisible. So for example, if we have 16 banks, we will be able to access the 16 banks at the same time if our stride is 1, but we will also be able to access the 16 banks at the same time if our stride is 3. And actually you could do the calculation for the banks that are being accessed if our stride is 3, and you will see that all the consecutive accesses are going to different banks. We are going to see an example in a little bit more detail, in this case for matrix multiplication. First of all, let's define the storage of the array that we are going to consider in memory. As I'm pretty sure that you know, depending on the architecture and also depending on even the programming language, matrices are stored in memory in a different way. For example, in C, matrices are stored in a row major layout. In Fortran, they are stored in a column major layout. And we definitely need to go for one of these two layouts, or maybe a different organization, because even though some data structures like matrices are two-dimensional or three-dimensional or even more, memory is a linear array. So addresses are always increasing linearly, right? So we have to figure out a way to map two-dimensional organization, two-dimensional data structures into this linear memory array. In our example, we are going to assume a row major order, row major layout. Here we have two matrices, A and B, and we want to multiply these two matrices. So let's take a look at how these two matrices are stored in memory. In our matrix multiplication. This is matrix A. Matrix A, this is A times B. Matrix A has 4 rows and 6 columns. Matrix B has 6 rows and 10 columns. So here we have six columns. So here we have elements 0, 1, 2, 3, 4, 5. This is element 6, and so on. Here we have matrix B. This is the first column. If this is element 0, this is element 1. This will be element 9 because we have 10 columns. So this is 10, 20, 30, 40, and 50. And we want to execute the matrix multiplication. So if we want to execute matrix multiplication, we have, as you know, to execute the dot product of row times column. So we are going to go through this row in this direction and through this column in this direction. If we want to use a vector processor to perform this computation, we will probably first go to this row and store it in some, let's say, vector register called A0, and we will store this entire column in some vector register, for example, B0. But how are these two, A and B, stored in memory? Because our memory is a linear array, so actually it's something like this. Even though it's a banked memory, from the point of view of the addresses, is still one linear array. So our matrix A probably will start here. So this is element 0 because we are assuming row major layout. This is element 0, this is element 1, element 2, and so on. And here we have element 5. So this is row 0 of matrix A, element 6, until 11. So this is row 1 of matrix A, and so on. And at some point in memory, we will find matrix B. This is element 0. Matrix B is also stored in row major layout. So this is element 1, 9. So this is row 0, and here we start with row 1 until element 20. So this is row 1. Observe that here in B0, what we want to store are elements that are not consecutively stored in memory. We want to access and store in the vector register this element 0, this element 10 and this element 20. So the problem that we have here is that even though for A we are accessing consecutive memory locations corresponding to this first row, for this first column in B we are accessing with a certain stride, that in this case is 10, right? Is that a problem? Well, it depends on the number of banks and how it relates to the stride. In this particular case, we have a stride 10, and if we consider the worst case, a memory in which we have only 10 banks, the problem is that all these elements 0, 10, 20 will be stored in the same bank. But also if we have, let's say, 16 banks, observe that 10 and 16 are not prime relatives. So 10 and 16 share some factors, right? 2. So if you calculate the addresses and the corresponding banks, you will see that some of the addresses that we need to access at the same time will be in the same bank. So we will still have some bank conflicts. So we cannot get full bandwidth or throughput from this bank memory. This is mostly what you have here in this slide. So different strides may lead to bank conflicts. And what should we do to minimize them or to avoid these bank conflicts as much as possible? There are different ways of doing it. The most naive idea is to have more banks. If I have more banks, I minimize the probability that two addresses go to the same bank, so I minimize the probability of bank conflict. But obviously this has a cost, right? So one possibility is to have a better data layout. And this will depend on the application, but in this particular case of the matrix multiplication, it's something that we can actually do. For example, what we could do here is a transposition of matrix B so that it will be matrix BT in memory. If we take this matrix and we transpose it, what we will do is this column B0 here will turn into the first row. So we will have element 0 here, 10, 20, 30, 40, and 50. So now our vector 0 is going to be stored in consecutive, all the elements in vector 0 are going to be stored in consecutive memory locations, 10, 20, 30, and so on. And now the stride here is 1. So we will have accesses to different banks for all these elements that belong to the, that are going to be packed in the same vector register. So our memory access will be much more efficient. So that's one possibility, but unfortunately this is something that it won't be possible always, right? It will depend on the application, it will depend on the characteristics of our data structure. There are some more sophisticated ideas, solutions in order to find a better mapping of addresses to bank. And one example are the randomized mappings. The randomized mappings essentially used some kind of hash function in order to find the bank where we are going to store one specific address, and in this way we randomize the memory accesses, and it's a way of minimizing the probability of bank conflicts. An important reference here, I think that Professor Mutlu already mentioned this work last week, is Bob Rao's pseudo-randomly interleaved memory in ISCAT 1991. So that's a very interesting paper to take a look at. Okay, let's continue. We will finish soon with this description of vector process and of SIMD processors. Recall that We distinguish in the beginning of the lecture between array processors and vector processors. Modern SIMD processors are actually a combination of both, including GPUs that are the prime example that we are going to cover in more detail in the rest of the lecture. Very briefly recall what we have seen in the beginning of the lecture, the comparison between array processor and vector processor. In array processor, we have an array of processing elements. All of them are able to execute the same operations and several different operations, like for example here, load, add, multiply, and store. In the vector processor, what we have is some kind of specialized processing elements that execute all the load instructions for all the load operations for one vector, or all the add or all the multiply operations for one vector. So in the case of the array processor, we have the same operation in the same time, different operations in the same space. In the case of the vector processor, we have different operations in at the same time. So we have different operations at the same time, and so sorry. The same operation in space, it's here, the same operation in space, different operations in the same time. And how are these instructions executed? So let's now take a closer look at the functional units. How are we going to execute this vector add here? In this vector add, we have two input vector registers, A and B, and one output vector register, that is C. How many units are we actually going to have? In a vector processor, we don't need to have more than one, actually. We could have one single functional unit where we start to input the different elements that belong to vector registers, A and B, and there we will have a deep pipeline, and after going through the entire pipeline, we will get the result. In this case, you have C0, in the next cycle we will get C1, etc. If we want more, so here what we are doing is essentially exploiting the parallelism in the pipeline. We are exploiting the parallelism by having different computations at the same time in different stages of this pipeline. We can have even more parallelism by having more functional units. In this case here, we have 4 functional units, and in each of these functional units, we can issue one addition, in this case, every single cycle. So here, for example, we start the computation of A12 plus B12, and here A13 plus B13, and so on. So assuming that, I don't know, in this example, maybe we have vector length equal 28. So what we will do is dividing these 28 additions in groups of 4 that are issued at the same time to the 4 functional units. So now we are exploiting parallelism in time and in space. Okay, and if we take a closer look at these functional units, what we will see is that they look like this. This would be like the vector unit structure. You see different functional units. Maybe this one corresponds to addition, let's say, and this one corresponds to multiplication. And observe that the source operands for these functional units are coming from some register file where we have the vector registers. We talk about a partition register file or partition vector registers because depending on the functional unit here, we will need to access the different elements of the vector register. In this case, this lane, because this is the name that each of the parts of the vector unit has. In this lane, we are executing all the operations related to element 0 in the input or output registers. Elements 1 will be here, elements 2 will be here, and so on. In this specific example, we have 4 vector lanes. And so what this means is that even though the vector length that we define in our code might be certain number, 50, it was in the example that we had before. Now let's consider that this vector length is 32. The number of functional units that we actually have, or the number of vector lanes that we actually have, doesn't need to be the same number. So in the example that we are going to see, we will consider a vector length equal 32, but only 8 lanes in each of the vector units. We have 3 vector units here, 1 load unit, 1 multiply unit, and 1 add unit. And every time that we issue 1 load instruction for 32 elements that are contained in the vector register, or will be contained in the vector register, what we do is doing it in 4 cycles. And in the first cycle, we execute for the first 8 elements in the 8 available vector lanes, in the next cycle for the next 8 elements, and so on. And assuming that we can have chaining here, as soon as we receive the values, these 8 values from memory, we can issue this multiply operation, this multiply instruction, and we can start working with the first 8 elements, and after 1 cycle we will work with the next 8 elements, and so on. So observe that, then we will have the addition. Observe that at some point in time here we are executing 24 operations in the same cycle. And if we continue the execution with 1 new load, and then 1 multiply, and then 1 add, if you count the total number of operations that are carrying out here is 192 in a total of 10 cycles. So it's really powerful, even though we don't have as many vector lanes as the vector length that we define in our program. How can we really take advantage of this? I mean, ideally, this is something that, how can we really take advantage of SIMD processors and vector processors, for example? This is something that we as programmers can do, but also compilers can help, because there are some cases where we can have some automatic code vectorization. Recall this example where we are adding the elements from 2 vectors. This is a vector add for n elements, and we store the result in ArrayC. Or a scalar sequential code would be something like that. For the first iteration, we load A, we load B, we add, and we store. For the second iteration, load, add, and store. It turns out that a compiler could notice, or a programmer, but the compiler can do it for us, a compiler could notice that there are no loop carry dependencies in this loop. So it's what is called a vectorizable loop. And if it's a vectorizable loop, this means that we can easily convert this scalar code into some vectorized code where all these vector instructions are executed, or all these operations that will belong to the same vector instruction are executed at the same time. So we will have 1 vector load here, vector add, vector store, and in a way that we are executing multiple iterations at the same time. Okay, we will go back to the programming of the SIMD processors, but meanwhile, let's have a very quick summary of vector and SIMD processors. We have distinguished between vector and array processors. We have seen that we can get very, very good performance improvement, but this is subject to the fact that we have regular data parallelism, and it's important to have this regular data parallelism, because this will ensure the vectorizability of our code. Recall the example of the CRAY 1. Even though the CRAY 1 was the fastest vector machine, it was also the fastest scalar machine, because the engineers were conscious about the Amdahl's law. You might have 1 million vector lanes. You might have an infinite number of vector lanes, but if a small percentage of your code is still scalar, inherently scalar, is sequential and cannot be vectorized, cannot be parallelized, Andal's law will be limiting the performance of your code. So I'm pretty sure that you're already familiar with Andal's law, and you must know, I don't know, for example, if 10% of your code is not vectorizable, the maximum speed up that you can get, even though you have 1 billion vector lanes, will be 10x. So that's why CRAY 1 was also the fastest scalar machine of its time. And now we're going to take a look at some current examples or modern examples of ISA, including SIMD operations. You can find SIMD operations in almost every processor nowadays. Intel has MMX and SSE and AVX instruction. In IBM PowerPC, you also have SIMD instructions in ARM. The example that we are going to discuss now is corresponding to the Intel MMX instructions as an example of SIMD operations in modern ISAs, right before we start with the GPUs. So, well, what the Intel engineers noticed is that there were many applications that could benefit from some form of SIMD processing. In particular, in the 90s, graphic processing, image processing started to become mainstream, started to become widely used, and that's why they decided to include these ISA extensions. In particular, MMX means multimedia extensions, because these kind of applications were the main target of these new instructions. And essentially what they did was defining some new arithmetic operations on short bit numbers. For example, here we can add 4 8-bit numbers by using one of these packed add operations in a way that from 32-bit register that can be used as a scalar register, what we do is dividing it into 4 parts, and in each of the parts we are going to have an 8-bit independent value. In order to do that, it was necessary to modify the ALU to eliminate carries between consecutive 8-bit values, right? Here you see the example A plus B, and the result stored here in vector in register S2. Let's see a more, here you have a little bit more detail about this. There is no real need to define a vector length for these specific instructions, because it's the opcode in the instruction, the one that determines what's the data type that we are going to consider. Assuming that our vector registers are 32 bits in total, we can have so are 64 bits in total. We can have 8-bit bytes, or 4 16-bit words, or so on. One important restriction is that the stride is always equal to 1. You can read all the details in this paper. But now let's take a look at this example. In this example, we want to overlay the human in image 1 on top of the background in image 2. This is what is called an operation that is called chroma keying, right? This is what you see when you're watching the TV, the weather forecast, for example. So here we have the weather woman, and this is our background. In this particular case is a blossom background, and this is the result that we want to get. If you want to see some sequential code for this, it's as simple as this. We will have to go through the entire image, X, that is this image with the woman and the chroma behind her, the blue chroma behind her. So if the corresponding pixel of the image is blue, then in the new image what we are going to store is the corresponding pixel in the blossom image. If it's not blue, because it's the shape of the woman, then we will store the original pixel. And that's what we can do much faster if we do it in parallel with some kind of SIMD processing capability, right? With some kind of SIMD processor. So for these kind of operations, these instructions were included in the Intel ISA. And here you see the very first thing that we will have to do is generating a bit mask. And with this bit mask, what we are going to do is evaluating this predicate. We need to compare the values in vector register MM3 that are coming from image X to a vector register where all the elements are equal to blue. With this pack compare equal byte instruction, we compare these two and we store in the output vector 0 if the corresponding pixel is equal to blue, or 1 if the corresponding pixel is, sorry, it's the other way around. 0 if it's not blue, equal if it's, 1 if it's blue. So then the next thing, once we have the bit mask in array MM1, we have to execute two more instructions, pack and that is here, and pack and not. Pack and is to mask the blossom image with the mask, and pack and not is to mask the woman's image. The result will be something like this. As you can see in the output vector registers, only those pixels that are really useful for us are remaining. So here, these pixels from the blossom image correspond to the part of the image that is the actual background. And these pixels here from the woman's image are the pixels that actually correspond to the woman. We finalize by ORing MM4 and MM1 in a way that we will get the final image. You have the code here, you can read more details in the paper, and yeah, but I guess that this is a good example of what SIMD processing is in current CPUs these days. And now let's go to the GPUs, graphics processing units that, as I said in the beginning, are let's say, the most successful type of SIMD processor these days. And actually, as you already know, they are some kind of combination of array and vector processors. We are going to see a little bit more details in the rest of the lecture. One interesting thing here is that actually one of the things that has made GPUs to become mainstream these days is the fact that now programming them is much easier, because we are not going to use SIMD instructions anymore. Now the way that we program GPUs is by using threads, and you will see how. We will go back to the parallelizable code that we were analyzing in the first part of the lecture, but before that we are going to distinguish between two important concepts: programming model, that is some software related concept, and execution model, that is a hardware related concept. And we will see what's the difference, and we are going to see how these two concepts apply to GPUs. What is the programming model? Refers to the way the programmer expresses the code. For example, you as a programmer can write sequential code, or can write some data parallel code, for example, in the form of SIMD instructions, or can write data flow or some kind of multi-threaded code with maybe OpenMP or maybe P threads in order for execution on a SIMD machine. That's a programming model. The execution model is how the hardware is actually going to execute the instructions that you write in your code. And the way that the hardware is going to do that will depend on the underlying hardware. You might have an out-of-order processor, you might have a vector or an array processor, you might have a GPU or a multi-threaded processor. This distinction is essential to understand what GPUs are these days, because in the GPUs we have a programming model that is called SPMD, SPMD meaning single program multiple data. Observe that we no longer talk about the instructions in the programming model, we talk about programs. And this SPMD programming model is executed or implemented by a SIMD processor. It's going to be an underlying SIMD processor. The good thing here is that we are going to have much more flexibility and still be able to achieve very high throughput thanks to the SIMD processing units. Now let's go back to the code. How are we going to exploit parallelism here in this vectorizable code that we had been discussing over the course of this lecture? Well, one way to exploit the instruction level parallelism here is simply use a SIMD machine, sequential execution, or we can go for a data parallel machine like a SIMD processor, or maybe some multi-threaded machine or multi-core machine, for example, MIMD type of processors, or SPMD. Let's start with the sequential thing. We can execute this on a pipeline processor. You're already familiar with pipeline. We can execute this on an out-of-order execution processor that allows us to exploit instruction level parallelism more by having some instruction window where we can have different instructions executing at the same time. Actually, if we execute this code in an out-of-order core, probably what will happen is that the out-of-order core is able to execute several of these iterations at the same time, because the out-of-order cores, as you know, they let's say they do some kind of hardware-based unrolling. This loop here would be dynamically unrolled by the hardware, because the processor can start issuing instructions that belong to different iterations. Another type of processor where we can execute this sequential code is, for example, a superscalar processor or a very long instruction word processor, because there are different instructions here that are independent. They could be packed into the same large instruction and be issued to several processing elements that will execute these operations at the same time. So this is the first programming model, the sequential programming model. What about a data parallel model, SIMD? Well, because of the fact, or because of the realization that each iteration is independent, we can have all these instructions or all these operations being executed at the same time. So for example, these two loads can be, or more loads can be in the same vector instruction. You already know how this works. We will be accessing array A in memory and getting some vector length elements from array A and storing them in the vector register 1 in this case. Then we have the vector load for array B. Then we have one vector addition. We add the element-wise addition and store the result in vector register 3, and then finally we store. So we can execute this on a SIMD machine, as the ones that we have already explained in this lecture, in a vector machine or in a vector processor or in an array processor. And the third possibility is having a multi-threaded code, a multi-threaded programming model, where instead of having a vector instruction, what we have is different thread of execution, and each of the threads is going to take care of each of the iterations of the loop. And this is what we typically execute on a MIMD machine. For example, if you take this code and parallelize it by using P threads or by using OpenMP, what you will be doing is creating one thread for each of these iterations. And same as we can execute this on a MIMD machine, we could also execute it on the so-called particular model SPMD, single program multiple data. And this single program multiple data is the programming model that the GPUs use and can be mapped, can be executed or implemented on a SIMD machine. So that's what GPUs do. Yeah, so GPUs are SIMD machines, SIMD processors, but instead of being programmed with SIMD instructions, they are programmed using threads. Each of these threads has its own context, so they can be treated independently. We are going to take a look at the details later. And the way that these threads that the programmer defines using this SPMD programming model are going to be executed is by being grouped into something that is called a warp or a wavefront. The terminology depends on what GPU vendor you go with. Yeah, we will call them warps in the rest of the lecture. So what the hardware is going to do is all these threads that you as a programmer have defined are going to be grouped in sets or collections of a certain number of threads, in particular 32 in NVIDIA architectures, 64 in AMD architectures. And these 32 or 64 are going to be all vector length and are going to be executed on the available hardware, the underlying SIMD processor or SIMD vector units that we will have in the hardware. Let's take a closer look. Now, this here, what in our SIMD processor was a vector instruction, now it's going to be the set of load operations that are going to be executed by the threads which belong to the same warp. In this case, you have warp 0, and then for warp 0, we will be creating the instruction for the next load, and then the addition for this warp 0, and then the store for this warp 0. So what we do as programmers is defining threads, assigning each of the iterations to the different threads, and then the hardware is going to take groups of these threads, group of, for example, 32 of these threads, are going to put them together in something called the warp, and they are going to be executed on the SIMD processor. Okay, yeah, let's continue. Here we have like the comparison of SIMD and SIMT, that is another way of calling the SPMD programming model. And there are two major advantages of doing this way. Let's take a look at them. The first advantage is that each thread can be treated separately. We can execute each thread independently on any type of scalar pipeline. We can do some kind of MIMD processing. And then we will see that it is potentially possible to group threads into warps flexibly. So let's first take a look at this first advantage. We talk about multi-threading of warps because GPUs are not only underlying SIMD processors, but they also take advantage of other processing paradigms. Of course, they are pipeline processors, and they are also multi-thread processors. We talk about fine-grained multi-threading because the way that the hardware is going to execute the instructions that correspond to the different warps is in a multi-threaded way. Instead of saying, okay, I have my warp 0 here, and I need to execute these instructions for warp 0. And when I say this, I'm saying these instructions, I mean this load, add, store. Instead of executing all the instructions for warp 0, recall that warp 0 is the collection of 32 threads. Instead of executing the first load for warp 0 and then the second load for warp 0 and then the addition for warp 0, what we are going to do is interleaving the execution of different warps. So that's why in this slide, this cartoonish representation, you can see so in one particular point in time, you will be executing load for warp 0, but then the hardware might execute the load for warp 1 and then maybe the addition for warp 20. obviously it cannot start executing the addition for warp 20 before executing the load instructions for warp 20. So if in this third cycle we see that we are executing the addition for warp 20, is because in previous cycles we already executed load and load. We already executed the corresponding operands from array A and from array B. So as soon as you access array A, as soon as you access array B, the next instruction, the addition instruction, is ready to be executed. But in the meantime, you are the hardware, the warp scheduler is issuing instructions belonging to other warps onto the hardware. Here we can see it in a little bit more detail. This would be a warp. We are talking about 32 threads. These 32 threads are packed together. They will execute at the same time. It is said that they are executed in lockstep because they always execute at the same time. And for this reason, they have a common PC. This is our SIMD pipeline here, and we start issuing instructions on this SIMD pipeline and executing instructions on the functional units that we have in this SIMD pipeline. And these instructions come from different warps. Warp 7, warp 8, warp 3. So maybe in cycle 0 we issue the load instruction for warp 0, and then the next cycle, in cycle 1, we issue the first load instruction for warp 1 or maybe for warp 20, and then the next instruction might be the second load for warp 0, and so on. The way that these instructions are scheduled is quite free, in the sense, and assuming that the dependencies are of course respected, but the warp scheduler has the ability to identify what warps are ready to be issued and then issue the corresponding instruction. Here you can see a little bit more detail about what would be an entire GPU. You have the memory here with the corresponding memory controllers and type of interconnection network, and the shader cores. These so-called shader cores are actually what we are calling the SIMD pipeline, or the SIMD cores. And within each of them, you can see that we have a program counter. Actually we have, as you can see, many instances of this program counter. We will have a different program counter for each warp. We can also have a mask, same as in vector processors we had our mask. We have an instruction cache here, we have the decode stage, and right after that we can start the execution on the SIMD pipeline that actually, as you can see, is composed by a number of scalar pipelines that represent each of the vector lanes. Recall the concept of vector lanes, that are all the different functional units that we had in the SIMD core. One of the advantages of the GPUs is that they execute this fine-grained multi-threading. Recall that I just said the warp scheduler is able to schedule whatever instruction is ready to be executed. We talk about eligible instructions. And observe that depending on those ready instructions or eligible instructions, the scheduler will decide, for example here, to issue one specific instruction, maybe a load instruction or an addition instruction for warp 7, and then for other warps, and then here warp 8, and then here warp 3. So this is what is called the fine-grained multi-threading, because we are interleaving instructions that are coming from different warps. And the main advantage that this way of execution has is that we are able to hide long latencies in some specific parts of the system. For example, when we access memory, obviously it's going to take longer than when we execute one addition or one multiplication, right? Recall our vector or example of vector processor, and there we consider that the cycle, the number of the bank access latency was 11 cycles. In current GPUs, the latency of a memory access from the SIMD pipeline to the memory, reading some value from memory takes hundreds of cycles. And that would be a problem, right? If we are executing one warp, instructions that belong to the same warp, and we have to wait for 200 cycles until we get some value from memory, and then we execute a second load and we get another value and another 200 cycles that we will have to wait, that will be actually very inefficient, right? Because we cannot start the next arithmetic operation, for example, an addition operation, we cannot start it until we get the values from memory. The good thing with the fine-grained multi-threading architecture is that while we have some warps that are going to memory to access data from memory, we can keep executing instructions from other warps that are ready on these cores that we have here, on these scalar pipelines that we have here, or these vector lanes in these ALUs. So that's what is called the latency hiding mechanism. We can hide long latency operations like memory accesses by executing other instructions that are that finish much faster and are ready to continue the execution much faster. So that's essentially one of the main advantages of GPUs when accessing memory. So yeah. You already know this slide, and actually we were using this slide when we were talking about vector processors. Now we can use it again to talk about SIMD, to talk about GPUs, because essentially GPUs are some form of vector or array processors. Now instead of having one vector instruction, what we consider is that we have one warp instruction, and this operation here, this addition of two elements A and B from arrays A and B and result being stored in array C, it's going to be the equivalent thing to the vector instruction. Instead of being a vector add, this is a 32-thread warp instruction. And instead of talking about vector units, observe that with the same picture we can talk about SIMD execution units and vector lanes in the GPU. So instead of talking about a partition register file, what we talk here is about registers for each thread. And remember, you might remember that in the previous slide, what we had here was elements 0, 4, 8, and elements 1, 5, 9, and here what we have are now these elements, but they are in the registers that correspond to specific threads. For example, thread 0, 4, 8, or thread 1, 5, 9, and so on. Also, this slide, we have just shown it before, applied to vector processors. Now we use it to explain how a warp is executed. Assume that we have 32 threads in each warp, but we only have 8 vector lanes. We only have 8 of these scalar pipelines in each of the SIMD pipelines that we have just seen before. So in the load unit, we issue the first instruction for warp 0. You see, now instead of talking about vector instruction, we are talking about warp instruction, or instruction for warp 0 in this case. We issued on the this instruction on the load unit, and we start the execution. Because we only have 8 lanes, we cannot start the execution for the 32 threads in the same cycle. We have to do it in 4 cycles. That's why we will be doing it in a way like this, right? So for the first 8 threads, then the next 8 threads, and so on. And in the multiply unit, in the next cycle, the scheduler could schedule one multiply instruction. And this multiply instruction, the warp scheduler has decided that is for warp 1. So here we will be executing the multiply operation for the 8 first threads of warp 1. And in the addition unit, in the add unit, we have an addition operation for warp 2. And then a new load operation for warp 3, warp 4, warp 5. You see? Yeah.
What's the motivation to have a larger warp size than Latency?
So there is, I mean, I guess that the real motivation for that, if you go to the for example, NVIDIA or GPU architectures, the real motivation might be related to engineering decisions. If you take a look at the evolution of NVIDIA GPUs, for example, you will see that the GPUs that were launched in 2006 or 2007 are like this one. They have 32 threads per warp and 8 lanes in each of the SIMD pipelines that they call the streaming multiprocessors, by the way. If you go to the next generation that was launched in 2010, you will see that it has 16 vector lanes for every 32 threads. If you go to the next one that was launched in 2012, there you have 32 lanes. But interestingly, in the last generation, if I'm not mistaken, they have returned to the 16 lanes. So, yeah, I guess that it depends on engineering decisions. There is no specific reason in terms of the theoretical point of view that we are analyzing here. Okay. One thing to keep in mind here is that the warp scheduler, this unit that is in charge of getting the instructions and issuing them on the hardware, on the execution units, the warp scheduler is not going to issue one, for example, multiply operation for warp 0 until the load operation for warp 0 has completely finished. I mean, if they both are depending on each other, if the multiply operation will use the output of the load operation, obviously. Okay, yeah, so this is a little bit more detail about how the threads are grouped into warps. There you in this figure you have 16 threads, and here we are assuming that the warp size is 4. So from 60 threads, the hardware creates 4 warps of 4 threads. Here you see some simplified CUDA code. That is, CUDA is a programming language to program GPUs. Observe that this for loop has been decomposed into this CUDA kernel, that actually the kernel is a CUDA function, and as you can see, the addition here is exactly the same. We read from memory an element in an array A, we read an element on array B, and we add and store the result in array C. Observe that instead of having a loop, as we have in the sequential code, what we have here is a thread ID. However, we calculate this thread ID, and then we will be accessing in A, B, and C the corresponding elements of the arrays by using this thread index. Here you have very similar code, a little bit with a little bit more detail. Actually, this is for a 2-dimensional organization of threads. As you can see, we have thread index X and thread index Y, because in CUDA we can define threads arranged in a linear way, or 2-dimensional way, or 3-dimensional way. Okay, yeah. In traditional SIMD, we have one single thread. We have sequential instruction execution, operations executed in lockstep. The programming model is SIMD. In GPU, warp-based SIMD, in principle, they don't have to be executed in lockstep, but actually they are, because these warps are SIMD units indeed. And each thread can be treated individually. And we don't need to know the vector length. We don't need to know. But we know, right? We know that it's 32, for example, is the warp size in NVIDIA architectures. But the programmer can define as many threads as he or she needs. And then the hardware will take all these threads and will start packing them and putting them together in different warps of 32 threads. The ISA is scalar because the way that we write the code is as every thread was independent of any other thread, and this is actually something that you have just seen in the previous sample code, and this is called the SPMD programming model. So in SPMD, define threads. They can synchronize at some point. We are not going to enter into this detail. Maybe in a future lecture we will have a chance to talk about GPU programming, but we won't spend time on that right now. What we are going to finish with right now is with the second potential advantage of SIMD architecture. Recall that the first thing has been that each thread is treated separately. The second potential advantage is that the hardware could potentially group threads flexibly. This is actually something that doesn't happen in current architectures, but wouldn't be that difficult to implement and would provide some more efficiency from the hardware point of view. And this would be necessary to increase the efficiency of the program execution, because the SPMD programming model allows us as programmers to write the code in the way that we want. We are allowed to write the code as if we were writing the code for a MIMD machine, because we are writing threads, and every thread can be doing a different thing. The truth is that if we really want to get the maximum efficiency from the GPU, we should try to have those threads that we know that will be in the same warp doing the same thing, right? But sometimes, because maybe we are not very good programmers, or because our program or application is so irregular that it's impossible to do, we will need to use control flow instructions. And when we use conditional control flow instructions, what might happen is that we have, let's say this is a control flow graph of our code. We will have threads which in principle are going to belong to the same warp. We will have threads following different control flow paths. For example, here we have thread 1 going this way through basic blocks A, B, C, E, and G, and then we have thread 2 that goes this way, and thread 3, and so on. So each of these threads are going through different control flow paths. And this is something that is not, in principle, is not allowed in vector processors, but here it's something that we can do. And the way we are going to do it is using something similar to the vector masks that we actually had in vector processors. This is the way that we are going to implement branch divergence. So here you see one example. This could be a control flow graph for an if-else. Depending on the value of a certain variable or certain address in memory, we could go, or one thread will go through path A or through path B. The way that this is executed is by using a mask. Actually, let me give you a very brief example here. Okay. So, in the slide, let's go back to the slide briefly. In the slide, in our control flow graph, what we have is the branch, and here we have path A, and here we have path B. And we see that some threads, we can consider that this is a warp, okay? So some threads of the warp will go through path A, other threads will go through path B. How is it actually executed in the hardware? So what we will have, this is, I don't know, maybe some instruction before the branch, and here we have the branch. For this first instruction, we have all our 32 threads that belong to the same warp, maybe, for example, warp 0, are executing all at the same time. There's no conditional execution for this instruction here, but then we arrive at the branch. I don't know, maybe in the branch we have something like if AI is even, for example, or if it's odd, we will go through one path or through the other path. So what we will do here in the branch is calculating a mask. So for all these 32 threads from 0 to 31, we will have one bit, 0 or 1, in the mask. And this maybe 0. Then the 32 threads go through path A, but actually only those that have 1 in the mask will be really executing. Maybe the other ones are also executing as well, but recall the simple implementation of the mask. They won't be committing the final result to the corresponding output register, right? So the actual execution is only for these threads for which the mask is equal to 1. And then we go through path B. So before going through path B, we have to complement the mask such that the bits that they were 1 before now are 0, and the other one, the ones that were 0 now are 1. So we will have now this thread working, and maybe someone else somewhere there. So this is how GPUs implement predicated execution. As you can see, it's a similar way to the conditional execution that we have seen before for the vector processors. And about predication, as I said, you will have more details next week. So what's the problem here? The problem here is that when executing path A and when executing path B, we don't have all threads working at the same time, all the threads of the warp working at the same time. So to some extent, we are wasting vector lanes, right? So one potential thing that we could do is grouping those threads that actually are active and can be a group because they don't overlap. The idea would be something like this, because recall, in GPUs, we have different warps working at the same time on the same instruction. So recall path A, we execute path A for vector, for warp 0, and then we will execute probably path A for warp 1, and then path B for warp 0, and then path B for warp 1. So if we have two warps, warp X and warp Y, that are going to go through the same path, one thing that we could do is merging them as much as possible in a newly formed warp, that in this case would be warp Z, in a way that we move these threads from warp Y to warp X, because the corresponding thread in warp X is not going to be executed because its mask is or predicate value is 0. Still, in some cases, we won't get any actual benefit because, as you see, still we have some overlap here. If we have some overlap, we cannot completely merge the two warps. Here you can see one example, what we could do for two warps, the blue and the pink or red one. In some cases, we can merge threads belonging to the two warps in a newly formed warp. And here you see one nice example of what we could do in the execution of an entire program. So this would be the baseline. Observe that there are many like empty slots because the mask is 0 for those cases. By using the dynamic warp formation, we will have dynamically formed warps here, you see, because there is an empty slot here. We can move this thread from here to here. Still, we don't get any benefit because there is some overlap, but in other cases, we will have some benefit, like, for example, for this instruction C and instruction D, where we are reducing 4 warp instructions into 2 warp instructions. And finally, we will get some savings in terms of execution time. Okay, yeah, we are almost very close to finish with the lecture today. This is just one last thought about this idea of the dynamic warp formation, because let me show you. Let me go back. Okay. Yeah, so observe here in this case, for example, we have a path A for warp 0, path A for warp 1. We see that we can form a new warp here because we can merge somehow threads from this warp 1 can be moved to the slots that are available in warp 0, but still we have the problem that we have some warps, some threads that overlap, right? So because we have some threads that overlap, we will still need to execute 2 instructions or 2 warps. But observe that we have some free slots still here, right? So we could potentially move these guys here, right? And then end up having one single warp or one single instruction. Well, this is something that we could do, and this is what this slide is about. Can we do it? Can we move flexibly any thread to any lane? Well, we could. We could if we allow the hardware to do it, and we add the extra hardware that is needed. But observe that the problem with this would be that moving one thread from this lane to a different lane would require to move all the registers that are the operands with which the corresponding thread works, and these registers might be a lot of them. So usually GPUs have like maybe 128, 256 registers per thread. So it's quite a bit of data movement would be quite a bit of data movement from one lane to another lane, which probably will kill all the potential benefits of doing that. Okay, this is almost all, except just a few last slides to show you some real-world GPUs. Here you have an NVIDIA GTX 285 that was launched in 2008. It has 8 cores. Each of these cores is what we have called a SIMD pipeline, and within each of these SIMD pipelines we have 8 vector lanes. This is an example that we discussed before. The pictorial representation would be something like this. Here, this would be like the entire SIMD pipeline, and here you can see the different functional units, the 8 vector lanes and in particular in each of these lanes we have two processing elements. One of them is for multiply operations, the other one is for multiply operations. We also have these on-chip storage, these registers that will be later partitioned among all these available lanes for the different threads. Here you can see complete big picture of the entire GPU. And here you can see a little bit about the evolution of the NVIDIA GPUs since 2009, when this 285 was launched, until 2017. This is the most powerful GPU up to date, and you can see how much the number of stream processors, that is the number of vector lanes, the total number of vector lanes in the GPU has increased from this number, maybe it was 240, right, until more than 5,500 or so, and also how much the total throughput in gigaflops has also increased. And this is the V100. It's a very, here you can see the entire block diagram. It's interesting because now in each of these SMs that are these SIMD pipelines, what we have called SIMD pipelines, you can see the different functional units. Like we have, for example, these are floating point 64, so it's for double precision operations. Here we have integer processing elements, floating point for 32-bit single precision, and then they also have this new fancy thing that are called the tensor cores, that are specialized cores for deep learning, for training neural networks. Essentially, they implement in hardware a super optimized matrix multiplication. Okay, this is all. Thank you very much for your attention. Yeah, maybe in a future lecture we can continue talking about this and introducing a little bit about GPU programming, but we will see. If you have any burning questions, or maybe we can keep talking after the lecture. Thank you very much.